So, welcome back. This is the last lecture of this course, second part on PDE. So, essentially I will be doing some general remarks here. Okay, so again let me start with some comments on semi group theory, and then so even for matrices or bounded linear operators in general, so if A and B are bounded linear operators, so they generate, that imply this e to the T A, e to the T B are groups generated by them, right? Generated by them. By AB. Okay. So, e to the T A plus B, so this is the group generated by A plus B. Okay. So, in general we know this T A plus B is not equal to E. Even for matrices we know this, right. So, equality holds if A and B commute. Okay. But it is always see, we have been discussing the semi group theory, and one particular operator generating a group, and then by some perturbation we also know that the other group, some addition operator also generates a group, but in general we do not have a knowledge of that group. For example, this considering the heat equation, okay, so we know that this group, semi group in explicit form, semi group is known in explicit form through that through Fourier-Poisson formula. Right. But if we make a perturbation here, so instead of Laplacian, if I consider Laplacian u plus some lower order terms, and of course we apply again Kato's perturbation result and show that this also generates a semi group, But it is not clear what that semi group is, though we know without lower order terms that explicitly. So, in this direction, so again many results have been developed. So, this is an important question, right. So, this goes by name of Trotter and then developed by Kato. So, they are now in the literature you find this Trotter product formula. Okay. There are many developments in semi group theory since that Hille Yoshida theorem was proved, okay, that after the discovery. Okay. So, one more few more remarks I would like to know. So, this we have discussed this heat equation, wave equation in particular. So, let me not talk about Schrodinger equation, whether Schrodinger equation in a bounded set makes physically sense or not, because you do not find any literature, but certainly heat and wave equation discussed only in Rn, right, only in Rn. But we know that these are also important, these problems, more generally parabolic equation and hyperbolic equations in bounded domains. What about in bounded domains? So, let me just bounded domains. Okay. So, more generally, so this ut we consider this Lu and utt Lu, where L is a uniformly elliptic. So, we replace Laplacian by elliptic second order. You can consider higher order also, but let me just make remarks about second order elliptic equation, elliptic second order operator. Okay. So, now you consider in bounded domains. So, bounded domains, omega. So, obviously, apart from the initial conditions, we also have boundary conditions coming from the this bounded domain. So, what is the strategy here? The strategy depends largely on the properties of this. So, that you have extensively studied in the first part of this course, weak formulation and then regularity theory, then even eigenvalues and other things. So, you essentially know many properties of that operate real. Okay. So, let me just recall that. Okay. So, again go back to the Hille-Yoshida theorem, then it becomes clear what we intend to do. Okay, okay. So, an operator A in a Banach space, A generates a semi group. This is most general one, of course. We have of course simpler versions in the form of Lumer-Phillips theorem. A generates a semi group if and only if. So, two things. So, A is densely defined closed operator, so most of the differential operators we encounter, this is easy to obtain. Okay. What is not that easy is this spectral analysis. So, that this there is an omega that sits in. So, a half plane or half line should be in the resolvent set and the resolvent estimates hold. Resolvent estimates hold. So, that so R lambda A, so let me write that. Of course, these are simplified when A is M dissipative, okay, that we have already seen that. So, this M lambda minus omega power k per k and lambda bigger than. Okay. So, this spectral this resolvent estimate is simpler for dissipative operators. Okay. So, this uniformly elliptic operator of second order should satisfy these properties. Okay. So, what should be the domain of that operator? Okay. So, let me again go back there. So, we should know the domain. So, of course, we are working in L2 theory, then the LP theory is again one more thing I just remarked. So, not much is known. So, there is need for unification. So, this is L2 theory. Okay, domain DL in L2. Okay, so, this is and in the first part you have essentially learned that L2 theory. Okay, and this domain should be such that it should contain the prescribed boundary conditions. So, let me just prescribed boundary. Okay. So, for example, so let me again go further. Okay. So, for example, for the Dirichlet boundary condition, ideal to consider this H1 0 omega, 0 Dirichlet boundary. And you also know when there is a non-zero Dirichlet boundary condition, how to convert that problem to a 0 Dirichlet boundary condition. Okay. So, that is and the hard part of the elliptic theory. So, even of course, weak formulation and obtaining a solution in H1 0 omega, that is also difficult, but more difficult part is the regularity. Okay. So, this regularity. So, actually the solution first you obtain using weak formulation gives solution in H1 0 omega, okay, but regularity gives actually U is in H2. Even for a general second order uniformly elliptic operators. Okay. So, that is the hard part. So, the domain in for this particular 0 Dirichlet boundary condition, we should consider this H2 H1 0. Okay. So, with this domain, now we can show that L is a densely defined closed linear operator. Okay. So, that is that part is that is fine, Okay. So, but more serious part, of course, this you can also do for higher order elliptic operators, and by the by an elliptic operator with real coefficients has to be of even order. Okay, that elliptic operators of order 2m. Okay, so they are always even order. So Laplacian is just order 2 and bilaplacian is order 4, etc. Okay. So the second part, namely the for resolvent estimates, the analysis is much harder. Okay. So, here one important inequality, lack of time did not permit us to do many inequalities, and this is one of them. So, this is Garding's inequality. Okay, let me just Garding's inequality. So, this is an important inequality in the theory, and that will lead us to this respect that resolvent set and resolvent estimates. So, all the inequalities you study, they are important in applications within PD. Okay, you need not even go outside PD. So, within PD, so let me just state this one for second order operator. So, this is kind of, you see already dissipativity here. Okay, so, this is LU L2. If you are working in complex space, we have to put a real part here, but let me okay, so just U in H1 square minus lambda 0 okay. So, that L is the same thing. Okay. So, this already we have seen many times, this cannot be avoided even for, if we just take for example Laplacian minus Laplacian. Okay, so, this minus Laplacian u, so integrate by parts. So, you get just this is L2 grad u square. Okay, I am just being so appropriate boundary conditions and this domain. Okay. Okay, so this obviously you see that u H1 square minus u L2. So, in general this for some constants C0 lambda 0 positive. Okay. So, but this is harmless in the sense, so we can add a lambda bigger than 0, and that absorbs this lambda 0 term. Okay. So, it is gone and we get a lower bound for, so obtain lower bound and that in fact proves dissipativity, and then you only we have to show that for lambda bigger than, and then one need to show. So, this essentially if you take minus, so you get dissipativity. Okay. So, this implies, let me write that, minus L plus lambda I is dissipative. So, in order to make it M dissipative, okay, so just so what we have to show is to make M dissipative, need to show that image, okay, this minus or plus, that does not matter here because we are taking. So, L plus lambda I may be some other mu I is L2. And again that you are back in weak formulation, and so that again go back to weak formulation and regularity. Okay, that is how you prove that the operator generates. Once we know that L plus lambda I generates, is not difficult at all to see that L also generates a semigroup. With lambda I is very good, okay, because this we know explicitly, okay, that is not a problem. Okay, so that so this is how you do problems concerning parabolic equations and hyperbolic equations with Laplacian replaced by more generally by uniformly elliptic second order operators and apply the semigroup theory. Okay, so you can see this again in Friedman's book. Okay, so this is a good source or any recent book, okay, by Bregis or whatever. Okay, so the M dissipative. Okay. So talking of M dissipativity, so let me just one remark, okay, just why that M, okay, M is for so suppose A is M dissipative, M for maximal, okay. So maximal for what? Okay, that is the question. So, okay, M is dissipative and B is any dissipative operator such that dA is in dB. Okay. No, not something more. Okay, let me write that. Okay, so B is an extension of and Ax equal to Bx for all x in D. Okay, so this is what we defined. So this, in other words, B is an extension of. So then A equal to. Okay, so you cannot have. So when A is already M dissipative, you cannot have any proper dissipative extension of P. So that is why that M maximal. Okay, so if there is one extension which is dissipative, then it has to be B. Okay, so this an easy exercise, you can do that. So final remarks about this course. Okay, so we have tried our best, I can say, to convey some topics in this modern theory of PDE, and in fact if you see the spectrum, it's quite large. So you have to really sit down and work hard to get best out of this course. Okay, so of course we have left many gaps in our arguments, and most of the time we have just referred to some textbooks, but to understand this modern theory, so this is only a beginning. Okay, so beginning, there are lots of things to do. For example, do not find much about LP theory in the literature, so that's one big topic. So there are many interesting things one can do. So we sincerely wish you all the best in learning this subject, beautiful subject, important subject, and having applications in many areas of science and engineering. Okay, thank you.